So, good afternoon, everyone. Welcome to the Crunch seminar. So before we start the seminar today, I just want to say something about the video recording. So recently I received some requests for the video recording of the Crunch seminar. So basically I record this all the presentation on the cloud, and then I will share you the link to all the video record. But I just realized that you only can get access to those record if you have a Brown affiliation. So if you do not have Brown affiliation, you are from out of Brown, so you can send me a message through this chat box on the right-hand side of this Zoom panel. So I will give you the permission to record the presentation on your local computer. So that's all I want to say. And with that, I'm very glad to introduce Dr. Sun. So our first presenter, Dr. Sun is Associate Professor at the Department of Civil Engineering at Columbia University, and his research interest is the material science, solid mechanics. And today he's going to share with us a very interesting topic. Basically, he used reinforcement learning to discover the weakness of constitutive laws. So Dr. Sun, welcome to join us, and please start your presentation. Thank you.
So Dr. Lee, thank you very much for your introductions, and thank you, George, again for inviting me for these seminars. So I would like to share some of the.
Sorry, can I interrupt you? Can you also say a little bit about your personal, because I have lots of students and so on. Can you say a little bit about your personal? Where did you grow up? I know you got your BSc.
Oh, yeah,
in,
sure.
Just give us a little bit of your
of my background,
of your history, your story, of your personal story before you go to the technical part. Yeah, because that's, I think students would like to hear that.
I haven't prepared that, but on the other hand, I've prepared it for a long time. So hi everyone. So I'm now associate professor at Columbia University in the civil engineering department. Before I joined Columbia, I worked at Sandia for 3 years first as a postdoc and then a senior member of technical staff in the mechanics of material department. So my educational background is the following. I graduated from UC Davis in 2005 with a bachelor degree. Then I have 2 masters, one from Stanford and another one from Princeton before I finally get my PhD at Northwestern in 2011. Yeah, and then I'm a native, as you can see, as you can hear from my accents. I actually grew up from Hong Kong, and I actually start my education in US, the undergraduate at the college in US, and I have been here working and doing research ever since. So yeah, I mean, I think this is my.
I want to add that Watchin, whose American name is Steve, has probably the most awards at this stage of his career that anybody I know in mechanics. So he's very modest, but he's very actually well deserved. Well deserved. He has accumulated already a lot of awards, more than anybody else. So anyway, that's great.
So George, I will add story in that regard that I heard from Professor Michael Ortiz. I think there's an old story about a soldier that get a lot of medal, and then people ask them, how do you get all those medal? And then the soldier said that the first one is by mistake, and then the other one follows. So in that regard, I feel very humble for the community support. And I also really happy to have the opportunity to give the presentation today. So without further delay, I can start talking about the talk that I'm planning to talk today. And this is basically combining 2 or 3 elements that are actually a little bit less utilized in computational mechanics. The use of the game as the tools to writing, verifying, and falsifying model, and the building of the knowledge graph that are able to help us interpreting the logic or the idea behind a constitutive model. So I want to first specify what is a game. So a game, I think a lot of us have a generic idea about what is a game, but here we would actually specify a game that have multiple components. It has a reward system. Okay, we can get different level of reward, like a binary win or lose, like the chess game or the Go game or Super Mario, that we get the score as a measurement of success. Or we can actually have another game that have more ambiguous reward that are not.
Excuse me, Dr. Sun. It seems your screen is frozen, so maybe it's not It's not moving forward.
Okay, let me.
The slides. Yeah, you can try to just stop sharing and resharing.
Yeah. Okay, sorry.
Okay, yeah, it works right now.
I understand why. Okay, thank you so much. So can you see the slide right now?
Yeah, right now we can see the chess. Yeah.
Okay, so this is, thank you so much, Dr. Lee. So there are different games that we probably play in live and we encounter. But if you think about it carefully, writing a constitutive model have a lot of elements that are very similar to playing a video game or playing chess and Go. And this is the following. We both are actually submerged to environment, and that environment could be based simply the reality. We conduct tests and we check how good we are on when we're writing a model, how much reward we can get. And from the reward, we can actually see how good we are performing, similar to playing the Super Mario. Okay, with that realization, the goal is that can we actually try to model part of the scientific process as a game? And if we can model it as a game, then that opens a very promising door in the machine learning world, because all those games that you shown here, except the last one that are less explored, are now actually able to pay by a computer agents with a reinforcement learning or some mixed strategy that allow the computer to make decisions that in the case of chess and Go are actually existing human player level. So if we can actually exploring that, maybe we can automate some of the scientific process and you hopefully superhuman results like the chess of and Go. So the goal of the meta modeling game is to build a system that actually have a self improvement capacity. We want to eliminate the scientific process by considering generating a material law as a game. Basically, for example, if you have a constitutive law, if you have a stress strain curve, how good it is as a focusing machine predicting new events would give us a reward, and we want to maximize that reward through the reinforcement learning. And another second goal is that we also want to understand, we don't want to build a constituted law that only provide a black box predictions. We also want to build a model that is interpretable and understandable by human. And first, we want to have the third ingredient, which is that we want the model to be able to improve over time, just like what we see here from the DeepMind. If you know how to play Go, you can easily see it from the pattern. At the very beginning of the Go game, played by the AlphaGo Zero, basically have a lot of movement that doesn't make much sense. It just try to occupy the center. But after 70 hours, it start to play like people have some experience of playing Go, that they understand the importance of occupying the corner. So we want to see whether we can rebuild that increasing, self-improving performance in an algorithm that we try to build and somehow replicate the behavior of a human handcraft model. The reason that we jump into that direction is also because we see that this is highly possible. Go in to write a constitutive model using the reinforcement learning. The reason is the following. If you look at the game of Go, the legal positions game of Go is much higher than chess. It's 2 to 170. So to give us an idea, all the atoms combined in the universe is 1.6 to 79. So with that large legal positions, the AlphaGo 0 can still actually change after 70-hour chain reasonably well, achieve a very high performance that we don't know. Now we're coming back, and then we go back to our constitutive model, and we try to, basically, we can think about the constitutive model as a linkage of informations. We try to predict kinematic law, and from the kinetic law, eventually predict the stress-strain relationship or displacement traction relationship. But if you consider all the variables that are somehow linkaged together, and we actually counted the approximate legal position is only about 5 million. Okay, so what actually draws us to this research is that if this can be handled, then the 5 million is very likely to be handled, and then motivate us to try to build the meta modeling game algorithm. And what we're going to show is some numerical experiment that we did after reviewing the algorithm, and also the extensions of building the competitive game to validating and falsifying the model. So this is actually the system. What we think about it is that we think the process of writing the constitutive model as a game. A game has certain ingredient. It has to have agents, and that agent can be a reinforcement algorithm. It could be a human, and then we make some actions, and that actions could be anything that you can think of to write a constitutive law. For example, if your goal is actually just to write a neural network model, that action may involve tuning the hyperparameter. Okay, how many neuron layer you want to have. What type of a neural network we want to use? Do we want to use recurrent? Do we want to use convolutional? All those decisions or action, or actually in the case of writing elasticity, what kind of, do you want to write it like a Neo-Hookean model or some other model? So those actions are actually the choice that take to write the constitutive model. And then what we actually build is the environment, is like the game board, where we actually compare the action that lead to the constitutive model, and then we have to automate building the constitutive model to the environment where it compared with the training data that the computer haven't seen before in the calibrations, but a new data set that are actually used to validate the predictive capacity of the model. And then depends on how good it is. For example, you can measure it using the inner product or the L2 norm that will give us the reward. And the reward is actually the reinforcement learning. What the reinforcement learning do is using that reward to give us a new policy value for the new type of actions that help us improve or write a different model. So if you can imagine that this is actually resemble the life of a PhD student. I mean, I guess when we start the PhD, we need to write a paper. Okay, eventually the reward will be the degree, and then we are giving some data, and then we write a model, we keep improving it. Okay, but one thing we notice is that as a human being, that cycle is limited. But with the reinforcement learning, if we know what is the actions, we can loop that cycle with the available computer issues much more frequently, or in a much higher, much more repetitively than a human can afford, until we reach a good model. So this is the idea behind the incorporations of the deep Q learning on writing the constitutive law. And one thing that we discover in writing the constitutive law is that in the history of writing the constitutive law, a lot of the new constitutive law involve discovering new mechanism. So at the beginning of the 20th century, we have the von Mises J2 parsiticity, and then that von Mises parsiticity is actually improved into Zucker-Prager model. And then there are new mechanisms discovered, and then we actually create the critical state model, and then with a 5-way tensor, we incorporate more microstructure information. But the idea is the following. If you think about the entire history in the last 100 years, is equivalent to have multiple variable, and then we try to find the right linkage to link them together, and then create a model. Okay, so the new model can be when we think about writing a new model, it can deduct into two processes: the discovering of new dependence or causal relationships, and then the explicitly writing of the relationships with some functions that link them together. If you actually thinking about it like that, then writing the model is equivalent to writing a direct graph that have the upstream as the unknown, like a displacement, and then the output as the stress. In the case of the traction separation law, the upstream will be the displacement and the downstream is the tractions. What we want to do is actually fill out the red curve out of all the possible way to link those internal variable together. What is the optimal way to actually create the right linkage? And that linkage also include a function that map the input to the output, and then lead to a model. Okay, so one of the important thing about this modeling approach is that we are not trying to directly link the displacement to the stress, because that will lead to a black box predictions. But instead, we're trying to finding the relationships among different variables that lead to the tractions. In this particular case, we know that the displacement will lead to the opening of the void space that increase the void ratios, and also change the coordination number and the fiber tensor. And the computer discovered that these three mechanisms are actually responsible to the tractions behavior and the response of the interface. So this is the main difference of this and the other black box approach, is that in the black box approach, what we want to do is that we will ignore all the internal mechanism that lead to macroscopic outcome, but instead we try to replicate the external behavior. Given that input, I want to get the output. We don't care what is inside. But in this new approach, what we are trying to do is that individually in each red edge, we can put a neural network there. But what we are interested in is not only generating the focusing machines that give the tractions, that actually predicting the constitutive law from displacement to tractions, but how do we actually, but the mechanism underneath it that lead to that particular tractions. So the goal of the game is that out of all the possibility, we try to deduct out of all the possibility that we actually mathematically written as a multi-graph, how do we coming out from a direct graph from the deductions. Okay, so the key is how to build the modeling game. So first, we need the data to build the environment. The environment that we actually use right now is actually coming from direct numerical simulation in the subscale. And in this case, we use discrete elements and then the ladder Boltzmann calculation to get the probability response and the displacement response, both for the interface and for the solid skeleton. That constitutes a database that used for the calibrations, and we actually have a cost validations that are used to measure the predictions capacity, and that one is cutting off from the calibrations data set. Then again, the goal of the game is that we have all the variable. We actually consider all the possible way to write a constitutive model. Whether it makes sense or not, we don't care at this stage, but we just consider all the possibility into something called a direct multi-graph. And the direct multi-graph in each edge, it represents the relationship, and inside each edge, there could be multiple ways to actually relate the variable. For example, we can use mathematical equations, we can use symbolic regressions, or we can simply use the known model to connect one physical quality to the other. The goal here is to put all the possibility here and let the computer figure out what combinations of the connection is the best outcome. So the reward system is actually measured by the cost validations. So there is a training data and there's a test data. What we want to measure is actually a score system that actually trying to put the test data with as little error as possible, but we also reward the consistency between the testing data and the training data. But there are other possibilities that can put into the score system, including the speed, the execution time, and also the robustness of the model. But the goal here is the following. Given a multi-graph, well, we want to find a direct graph that can be converged into a training program or actually a model that, that lead to the best performance. So like the game of playing Go or chess, writing the modeling game also have its own rules, and that rule is the material principle. There are some universal principles you need to obey. For example, I think we need to make sure the model have material film indifference. In other words, objectivity. And this is one example of the importance of it. If you have a strain and a stress, it's actually important that how do we represent that strain and the stress, and not only would affect the learning rate, but also affect whether the resultant model will be dependent on the coordinate system that we choose. And here, what the technique that we use is the following. If we try to generate a stress prediction from the strain would have we would actually conduct a polar decomposition on it, and that will lead to a principal stress and the rotations tensor that actually, and then the rotation tensor between the predictions and the benchmark are actually going to measure in the using the Lie algebra. This is actually one simple technique to actually measure to ensure the results are actually material film indifference. And notice that, I hope that I can, okay. So this is actually the results of a crystal plasticity model. If we do it in a component-based model, the eigenvalue are very easy to predict, but the spin actually due to the activation of a slip system is going to be missed in the component-based training because the learning rate simply cannot pick up the sudden rotations that are actually occur when the plastic slip system are actually activated. So we can think about, so for people not familiar with crystal plasticity, you can think of it as a stack of paper that are actually lumped together. So maybe, for example, like this book, if you actually try to sharing it in different directions, I will get a different response. And the activation of the slip system is like the paper stack direction getting shear. Okay, once it's shear, the principal stress, of course, rotate, and that require a special treatment to actually capture that. And then there are other mechanical restrictions as well. Film indifference is one of them, thermodynamics. And then the logic is the following. We will use the Monte-Carlo tree search. In each time step, in each episode, when we train the model, it would actually go through a self-play process in which the computer agent would make a decisions about connecting the internal the variable in a different way until we get the model. The model will actually compare with would actually make a few predictions on the unseen data, and then how good that prediction is going to create would have a loss functions. And the important thing that actually departure from just a supervised learning is the following. The score would actually help propagate back into each individual decisions that we made earlier in connecting the direct graph to give us the reward of each individual actions. And and the goal of the reinforcement learning is to improve our estimations of the reward of each actions until we actually paid it enough, we sample enough so that we can reasonably estimate the accurate reward of each actions. So we compare the modeling of game with the chess, we can see the similarity. We make a sequence of decisions. We have a game board, we have an action space, we have a game state about how as we connect the model, and then we can move the chess piece, but we can also make decisions subject to the universal principle, like how the game piece move. And then we can get a modeling score, and then we can also using it to improve the game. So I just want to show some results. This is actually one way to modeling is that in that game, there is no neural network modeling technique used here. We just want to compare different regressions results, and we want to see how does whether the model can recover the known model. So as you can see, with the data is completely artificial. We just generate the data from the model, and we see whether if we don't give the computer agent any information, whether it can recover the underlying model. And so we can see that the J2 Jupyter and the free invariance model all converge really fast. After 10 games, it actually discovers all the underlying mechanisms of the model. And then we also validating this. We can also doing it in the finite element stage where the model continue improve until the benchmark, and then the model are actually identical. Now, in the other case of the Jackson separation law, we would actually pay the same game, but there is no underlying model that we know. So what we actually did is that the edge are actually connect simply by LSTM neural network. So at the beginning, the model, you can see that it did a very poor job. Sorry, I don't know what happened to the. At the beginning, the model actually did a very poor job, but as it improved, writing more and more model, the neural network, the agent is actually improving the skill and writing better and better model until the predictions and the by prediction all yield very good results. We can look at the modeling score. At the beginning, there are some good performance, there are bad performance out of all the data. But as the game is actually going on, and then the computer exploring different actions that can lead to the better model, eventually it leads to the point where the model are actually universally converged into the pitch score. And the performance and are also getting more robust. As you can see, the maximum and minimum of the model are actually also reducing.
So can you go back to the previous slide?
This one?
Yeah. So the blue is okay. The red is the.
Yeah, the red is the DM.
Right. That's a multi-value function. How do you find that? If I take a constant v, let's say 2 millimeter displacement, I have multi-values of the stress, right?
Yeah. Yeah. So this is not necessarily a scalar. This is a vector. So the nodes are vector. So when we train it, it's actually, so here, for example, this is a displacement vector that are used as an input to, so this you can see that two component in the orthogonal basis. And then we're using this to actually predict how does the fiber tensor are moving. So this is just showing one directions in the normal direction, but we actually train all the different directions together. Just like a stress strain curve, we train all the components together.
Okay.
Yeah, so it's not a 1D simulation. So thanks for asking this. This is very important. We are not training it separately. So they are actually trained whenever there's a vector or tensor, they are training it together either in the treated as one entity in the nodes. So we can seeing that improvement, and also the mode is not purely 1D. If you look at the, I only have the normal direction here, but we also try mode 2 and mode 3. We can see it in the later versions. So we want to expand this a little bit, and then we want to actually build something that are more interesting. And this is actually moved away from the robotic. Okay, this is actually a very interesting paper in 2007. And the goal is to train the one robot arm to grab something. But what they actually discover is that if you add another robot arm that try to actually prevent that red robot arm from grabbing something, over time, as they compete against each other, the red robot arm will find a more robust way to grab something. Okay, so this is actually, this would be better than just have one robot arm trying to learn how to grab a ball, because it has to figure out how to find a way in the existence of an attacker, how do we still complete the ongoing task. So what this one, consequently what they did is that if you find a rule that can achieve that can not only achieve the task but with better robustness, which is important for material model because when we write a material model, we don't want to cherry picking only the good result. We also want to know the worst scenario. For example, when you build an aircraft, constitutive model for composite use in an aircraft, we want to know the model is good universally, what we hope, but we also want to know whether there is any hidden spot where the model cannot capture the reality. I think this is also important for building the digital twins. We need to know when is a weakness or when does the model fail to predict the reality, and we want to pinpoint that area of weakness. So that leads to the second part of the research is that we try to build, instead of one agent, we try to build two sets of agents. One is trying to have, they are both experimentalists, and what they did is that they try to design an experiment. One used to calibrate and validate the model. Another one tried to attack the model, making the worst case, making the model look as bad as possible. And then they're competing against each other, just like the robot arm case. And we want to see over time as they play more and more game, what would happen, what will be the underlying dynamic of the game, and what will be the consequence of the game, and what happens if you take out one model and just have the other model. How does the dynamic change in that non-cooperative game? So the idea is the following. Here we have a known model. We don't touch the model, but we only calibrate the material parameter, or actually retraining it with a fixed knowledge graph. But we change the actions of the agents. Now the agents are experimentalists, so it can design multiple parameter. How do you want to design an experience? It can have different confining pressure. It can lower it in different void ratio. It can prepare the test into different loading path, extension tests, compaction tests. It can have different loading and unloading targets. So each walk in that decision tree represent one experiment. This can be a physical experiment or numerical experiment. And then in each time, each agent can make a walk into the decision tree to generate one experiment. And then the experiment is used to either calibrate or attack the model. So the reward is the following. It's a non-cooperative game. So we will use something that a coefficient index to actually measure how success the model is. The model will be most success when the efficiency index is 1. If it's 0, that means that the model is just as good as the mean observed data. And then if it's less than 0, it's performing even worse than the mean. Okay, so the score is actually identical. We just renormalizing it to -1 and 1, but we actually want to make the adversarial and the advisory and the protagonist reward being opposite to each other. So both of them have a score, but one would, and then for the protagonist, we also have a decay rate, meaning that it have a discount if it cannot. Not only does it need to score higher, but then if you don't score better than the historical value, the action actually have a discount reward. And we play this game with the same reinforcement framework. Each time we generate predictions, and then the reward will be assigned to both experimentalists to motivate them to design a different experiment over the time. And this is a numerical experiment we can see from the Juker-Prager model. At the beginning, the motion is pretty random. Basically, have just randomly picking a walk in the decision tree, and then we try to calibrate the model. You can see that you don't see much strain here. Okay, after 5 iterations, after they play the game 5 times, you start to see the ongoing pattern from the defender and the attacker. The defender increasingly would choose a simple pattern to show the Juker-Prager are able to model a monolithic loading and unloading case. And the attacker would actually focus on the cyclic loading. This is actually just a well-known example. We already know that if you have a Juker-Prager model and we only have isotropic hardening, it's not going to model the cyclic model response really well. What we want to do here is actually just to show that we can recover the conventional wisdom.
Can I ask here, Steve?
Yes.
How did the attacker go into these hysteresis loops?
Sorry, can you?
How did the attacker go into these hysteresis loops? What prompted?
Oh, what prompted? Okay, so let me explain it a little bit better. Okay, so it has a decision tree. So both of them are, imagine that the attacker and the defender are both experimentalists, and they are given the same decision tree, which means that it's like a manual of the experiment. It can design the experiment whatever they want. You can design that you want the loading, you want to have loading until certain point and then unload and reload, or you can just stop the tree here, having a monolithic loading. So the game is like Super Mario. It has a bottom. So here the experimentalists also have a certain leverage of designing the experiment. Anything in the work is actually legal actions, legal experiment they can design. So they can design whether they, in this case, because we're giving the action of unloading, the experimenter can design whether they want to unload or they just want the monolithic. So, and their actions are based on the reward. They try to maximize the reward. In the case of the modeler, there is no reward for them to do the unloading because the Juker model is not good at unloading a cyclic loading. So it doesn't motivate them to have the reward. But for the attacker, so eventually what they want to do is just keep trying to show the weakness, and that motivates them to actually visit this part of the decision tree.
So, I see. So is it because of the non-cooperative type of
because of the
game?
Because the reward are exactly opposite. Because the reward are exactly opposite. So one scan is
because if it was a gun, it would not be like that. But I think the non-cooperative takes it away from
exactly. If they're cooperative, they would hide the weakness, and then you won't know that. But because they're non-cooperative, so the modeler, I mean, it's like we go to the PI meeting. Sometimes we want to ask tough. I mean, I don't know. Sometimes we ask tough questions just to find out what is the weakness, and this is exactly the case. And you can see that other tendency. Okay, so this is for the other two model. For the Juker program, we have a pretty clean cut. For the binding service model, you can also see how does the attacker and the defense choose the different actions. Usually, the defense will choose simpler actions that they can make the model look good, and then the attacker will focus on the worst case scenario. But we also have some case where the attacker, the interesting thing is also the dynamic, because after each episode, after each run, the model is recalibrated with the new data. So as the game going on, you can see the relative success of the attack and the defense change over time. So you can see here, initially, the attack is actually doing really well. So the attacker is actually able to find out some weakness that are really bad for the same material model. But as the iteration keep going, the model get recalibrated. And ultimately, the worst thing that the attacker can do is the last data, is the last attack that you can see in iterative 10. So you can see the dynamic as you giving more balanced information, as you know the weakness that discovered from the attacker also help the game to actually find out the better solutions to modeling action that are actually cannot be discovered from purely optimizations. So because in the optimization game, you don't see the reward of actually doing that, because you can see that if I cherry picking the reward, all the predictions look very similar. The difference on the behavior in the non-cooperative game is that as the game going by, the material become more robust in the worst case. So this is the worst case at the end. This is the worst case at the beginning. You can see the difference. We can look at the Q table and then the actions. Initially, because the Q table is randomly assigned, so you can see the heat map. You did not quite identify the strength and the weakness of writing the model, but this is the defender's game. At the end, you can see the the red zone is concentrated in certain type of loading that can benefit the calibrations. One thing we also find it interesting is that adding more data doesn't necessarily make the defense stronger. Sometimes when you have all the data available, a subset of the data may actually lead to the best outcome. So we can see the three different known models. One is two of the known model and one of the machine learning model, and they have relative success. The Geotechnical game basically pay as expect. So we remember that the attacker, the reward is actually the game score -1. So in this case, both of the game get what they want, it looks like. But what actually happened is that if you want to cherry picking the good result, the Geotechnical can give you a very good match in some part of the decision tree, but not everywhere. But you can also find a very worst case that the model actually absolutely cannot do something in that decision tree. In the binding surface case, because it has a kinematic hardening mechanism, the worst case is actually getting better. But you can see in the last case, when we're running the machine learning model, we can actually, the attacker basically did not get much reward compared to the defensor. You can actually see this is something that quite interesting, because a lot of the machine learning work, the conventional wisdom is that the machine learning model tend to generate less robust results compared to the conventional model, but this shows that this is not necessarily the case. In particular, in this case, you can see that the machine learning is actually able to generate a result that is pretty robust. Even the best attack will still give a positive score that are actually showing that it's better than the mean values. So this is encouraging on using the machine learning. There are some future research that I would like to mention. So what we show here in the previous 40 minutes, 45 minutes is basically the technique of using a direct graph and the knowledge graph to make decision-making part. We haven't talked about is the geometric learning. How do we also use the geometric learning to generate new descriptor and incorporate into the modeling game to make better predictions? Or another generic way is that can we reconsider parasiticity model as a level set problem? And if we can consider it, then we can generate any arbitrary U surface that are hardening in any arbitrary way, and therefore unify the existing elasto-plasticity model. Another thing that actually coming from the efficient index is that in some time writing the model would not be very meaningful if the data is actually scattering around. If you try to actually write a model in that probability curve, you probably get something like this. But then that would not be very predictive because the data are very scattered. So in that case, we also work with my other student, Bahado, to work on the model tree. So we can think about it as a way to expand the strategy we use to actually make a predictions. Not necessarily in this case, there is no model. This is more like the work that relate to the data-driven model tree approach. But we can think about it, incorporate it as options in the strategy, and we can rethinking that, making the predictions as a game where we try to predict a maximum outcome with a discrete course of actions that we're going to make. So this is actually the 4 paper that relate to the meta modeling game, the cooperative game that have the experimentalists and the modeler work together that we don't have time to talk about too much today, and also the non-cooperative game where we try to introduce the attacker that actually make the model world more robust. I want to end this presentation by thanking the sponsor of my research, Sandia, DOE, NSF Korea, of course, Columbia, Army, and Air Force, including a recent movie project on interjecting material. So, of course, I want to thank the host again, George and he for hosting me, and I welcome any questions. Thank you very much.
Hi, this is
Thank you very much, Dr. Sun. So, yeah, I see our audience have some questions. So go ahead.
Hi, this is Leo. I'm a PhD student in Consequently. Thanks so much for giving the talk. It's very good job. So I was wondering, like for example, in the first part of the talk, I noticed that the deep reinforcement learning iteration is like only like 10 iterations, which is much less than what I expected. And I also like noticed that it seems that there is also like a black box neural network in to represent the connection. So I was wondering if the gain comes from the graph or this kind of black box black box neural network. Or in other words, so firstly, what if I change the graph a little bit and then train the neural network again? Can we still get a good good regression result? And secondly, is the graph really interpretable? For example, like if the can we do dimensional analysis on this? Like are the units correct? So that is my question. So yeah.
Oh, thank you for the questions. I hope I remember all of them, but let me try to provide the answer one by one. The first question is yes, no, yeah. The first question is why is it only 10? I think that the reason that so there are more than 10 tries, but there are 10 iterations. So, the reason for that really increase on that is because those data is actually coming from a model data, and hence this is very simple to discover. Unlike the experimental test that doesn't have a very clear train for the or actually marry with some noise. I think this is the main reasons. And again, this is actually the rhetoric stress and the strength. So the prediction is actually on the full tensor and the full string. If I understand the second question correctly, is it possible to have multiple graphs that create similar results?
Yeah, exactly.
Yeah.
Sorry, I didn't make myself clear.
No, it's okay. Yeah, I think, yeah. In general, it's possible. Okay, the important thing is that in each test, so this is kind of like a boxing game. So in this episode, we play 75 episodes. That means in one episode would have one model. You can think about it like a boxing game or tournament in which the winner eventually is used to as the focusing machines. It's possible that in principle, it's possible that two models can have the same score. But what that would mean is that they have equivalent prediction capacity. So, but if the score are different, then we will just simply pick the best one. If the score are actually identical, which is pretty hard to achieve, then that means you have two alternative theory that are actually generated from the graph. And from the prediction alone, from the objective alone, you cannot distinguish which one is better. So that would be the very rare consequence, but that may happen.
Yeah, and then I mean, as there's still another question that is like, can we interpret the graph? I mean, I'm not sure if there is any like units in for these quantities. So for example, are the dimension analysis correct for like in this graph?
I don't understand why do we need the dimensions, because those graphs are actually telling you that. So maybe I can explain a little bit further using a bigger picture. So for example, here, maybe I will pick something even simpler, like this one. Okay. So porosity have no unit, coordinates number have no unit, fiber tensor have no unit, but some of the physical quality may have unit. But what actually happened is that, let's say this is actually the graph we determined from the modeling game. What happened is that in order to predict the tractions, we will look from the upstream. We know that we need the fiber tensor, we need the porosity, and we also need the displacement jump component in two orthogonal directions. I would build a neural network that take these three as input and then output the tractions. Now, however, because we don't have the fiber tensor predictions in the get-go, so what we need is that we would create another predictions that using the coordination number and the displacement jump as an input and output the fiber tensor. So you can see that this is a big direct graph, but in order to create the predictions in sequence, we need to identify each subgraph in one generation back for each nodes until we actually visit the roots. So there are multiple predictions there. It's not one neural network. So for example, in this case, porosity would need one neural network if you're actually using a neural network to make the predictions. But here for the coordination number, I would actually basically need the, sorry, if you look at the arrow, the coordination number would use both fiber tensor and the tractions and the displacement jump as an input.
Okay, I kind of get that. Oh, okay, thank you so much for
no problem.
Yeah. Thank you.
Dr. I have a question. My question is, can you comment on how the probabilities within the nodes cause and effect inference on the graph affect the final outcome or reward and how does the probability get generated on different nodes on the graph?
Okay, so let me repeat the question if let's see if I understand. You're saying whether the initial configuration would affect the graph, will affect the outcome?
Yeah, like how does the probability affect the outcome based on the graph, like within the nodes? And how does the nodes, I mean, you go from node to node, you have a probability, right? So how does that probability affect the final outcome or reward on the reinforcement learning?
So okay. So initially we don't know how this thing is connect. So the connectivity is just assigned randomly based on due to the fact that the key value are completely random. Okay, so that means that we can start with different configurations at the beginning. And what we want to see is that we want to see at the end of it, whether we will converge into one single configuration. So that is an optimization problem. So in principle, it's possible that if you have a loss of local minimizer, it's possible that you can end up with different configurations. Okay.
Okay, so you just shows random parameters, random numbers, and then you run it.
This is random, but there is also another thing that are used in AlphaGo that are very important. Remember that when we actually design the next course of actions, we are not just trying to solve an optimization problem. We want to balance the exploitations with the explorations. So there's a random value that we also assign to actually balance the results. And this is actually called entropy or temperature in the original AlphaGo paper. And this is actually when we actually increase the temperature, it encourages the exploration so that it can avoid us to actually trap into the local minimizer. But what we actually did is the following. In the very beginning, we let the temperature remain high for a while. And then towards the end of the game, when we know that the exploration, when we have an estimation that the exploration is enough, we cool down that temperature parameter so that it will look for the local minimizer. So that can actually, that would actually give us some, this is not exactly, we don't know whether this is exact the best way to actually avoid the local minimizer, but this is a way that have been known to be successful for the Go game. And that we are just simply using that same technique.
Okay, thank you. So you you switch the graph based on the data, and then you get like the best outcome, like the best reward, right? Based on the configuration that works best for all the steps that it goes through, right? Through all the graph, or through all the all the environments, type of environments, right?
So sorry, I don't get the questions. Can you?
Oh no,
I'm sorry.
Oh no, I was just saying that you go through different, like you have different explorations, right? You explore different parameters and different configurations, and you just reach the one that was the best for your problem, right? Like the
Yeah,
best configuration.
yeah. And again, the best is a relative term. We can actually put different reward system there to get what we quantify as the best.
Okay, thank you.
Mhm.
Hello,
Steve, I have
Dr. Sen,
a,
yeah, go ahead, George.
no, you go ahead. Sorry,
Okay.
you go ahead.
Dr. Sen, I had a question that, so you have this initially directed multigraph. So you represent the relations between the nodes using a neural network. So as part of the actions, does the agent also update the parameters of hyperparameters of
Yeah,
the neural
yeah,
network?
exactly. So no, sorry. Let me answer the question. So it should, in the paper that we have, right, we haven't tried to do it. But this is also something that that is actually why we write it as a direct multigraph, because we don't necessarily know how. We know that the connection is there. We don't necessarily know how to connect it. What is the best way to connect it? So it should connect. I mean, once we find out the connectivity, then the next task is to find out what is the best way to make the focusing and small focusing engine in each subgraph. So in principle, the hyperparameters should also be retuned. But here we just put it conceptually. This is a multi-graph, and then we don't know how to connect it, and then we just show some possibility. So in one paper, we connect all the graph in new network. But we also have another paper published in Computational Mechanics in which we don't use any neural network. We use the symbolic regressions. And then, like what you said, each time we have to recalibrating that parameter in the case where we use the regressions, symbolic regressions. So the hyperparameter should be tuned, but then that would slow down the graph. So this is also another thing that, that if we actually including tuning the parameter, then the modeling space would have more legal action than 5 million. I think that would probably skyrocketing it. Yeah, but you can count, maybe you have 7 to 10, I don't know, hyperparameter to tune, depends on how compact it is. And
So
you can do the math how much more compact it is.
So, like for the symbolic regression thing, does it work well? I mean,
yeah, I mean, okay, so this is also another interesting thing. So we play around with some symbolic regressions. I think that it could possibly work, but it's actually sometimes you need to expression that look as complicated as the neural network expressions. So what we did in the symbolic regression is that we actually fix a lot of, we actually limit the choice a lot in the symbolic regression. We only use the form of the equation that have been used in the literature. And we force the computer to only pick those things in the literature. So the decision is still the decision is actually still discrete and can be described in the decision tree. If you use the revolutions algorithm, you may actually deal with continuum. Your decision can be continuous and you cannot use the decision tree approach. But here our focus is on the discrete decision making, not continuous. But in the future that may be considered. But so here in this example, what we try is just in the action space, we only have all the known mathematical possibility equation form that that human has used before, and then we put it into the multi-graph. So we found that one more actually easier to have success. But we are not the expert of the symbolic regression as well. So there may be other trick that we can discover along the way.
cool. Just one more question that so you said about the constraints, right? Like in the game of chess, we have some constraints. Similarly, you
Yeah.
had constraints here. So, like, do you pre-code those constraints in the multigraph, or you like take care while training?
Yeah,
The
so this is
network?
actually one thing that I'm really glad to ask. Okay, so there are two different strategies like you actually already hinted at. You can put it in the score because if for everything that violate the constraint, you can actually put a penalty there. Like if you actually predict a negative dissipation, you can actually give a very low score to motivate the computer to do something else. But that would also make the landscape of your score in the parametric space more complex. So what we actually advocate is trying to do something that already fulfilling the thermodynamic constraint in the individual component. So like the material frame indifference, if you're doing it, if you're actually using the Lie algebra, there's no point that there's no reason that you can violate that constraint. The same thing if you have a isochoric Parsec flow, if you're doing it in the right way by using isochoric formulations, then there's no way you can violating that. We're finding that constraining the mapping or the action space that already fulfilling the behavior is easier than putting a lot of things in the multi-objective optimization problem. There's also another motivation for the future work on the level set modeling of the plasticity. One thing that actually nice about the level set approach is that, and this is done by my new student, Nicholas Venice, is that some of the constraint, like the thermodynamic constraint, if you're actually writing it in the right parametric space, it can convert it into a geometrical feature, like the relationship between the convexity and the dissipations can be established if you can actually write the U surface in the principal stress space. So this is some of the ongoing thing that we are exploring, not just to fulfilling the thermodynamic or the physical constraint, but what is a smart way to do so without making the learning problem harder.
I see. Okay.
Yes.
Thank you. That was very, very nice. I just want to say that the Prager model was actually developed in our department. It was Prager.
Oh yeah.
Was the founder of applied math at Brown, so that's where this model was developed. But I have a question sort of at a high level, and one of my collaborators, Eric Darv, I think with Charbel Farhat, they wrote a paper where they were trying to discover the constitutive law for rubber.
Yeah.
And so they do the usual numerics, finite elements, and then on the constitutive law, they just have a black box neural network, and the neural network discover the constitutive law, and it does much better than they.
Yeah.
So if I compare, why would I not do that? Why would I? What was the convincing argument to use this game approach as opposed, because that curve, for example, that you show, the Drake-Prager curve is very simple. It's a very simple model to learn. So why would I use this approach to learn instead of what I just described, like a black box neural network?
Yeah, thank you, George. I think this is an excellent question. There are multiple ways to think about it. So one reason of introducing the intermediate nodes that actually not so obvious, but are actually quite important is how generalized the model could be. And basically, we are studying a different learning problem. I can give you an example of this. If I try to create a black box, then what I actually mean is that I will create a black box of one RVE. Okay, I have one RVE that have exactly one initial porosity, one fiber tensor, and one coordination number, and I actually run that lots of tests on that RVE, and eventually I can predict the stress strain curve with the black box, and then we can generate lots of good results. However, in this case, we are not training one RVE for one. We are not training the model for one RVE. We are training a model that can capture a family of RVE with different initial void ratio, how many space it have in the porous media, different fiber tensor, and different coordination number. So this is the goal of the game. The model that we generate in that sense is actually more generalized. Because the model is not create one circuit model, but by actually allowing us to describe the initial configuration and the configurations differently, we can actually capture a family of different modeling behavior of model, which is actually closer to a human model. When we try to write a Drake-Prager model, or actually maybe maybe a crystal plasticity model, you don't want to generate a polycrystal plasticity model only for one configurations. You want to generate from multiple different configurations so that in each time you have a new microstructure, you don't have to rewrite the model. So this is actually the one of the underlying importance of it. Another one is basically another recent big thing that I think is important is that sometimes you don't necessarily just want to make focusing machines. The focusing engine is actually very attractive, of course, has its own values, being very useful. But sometimes you also want to understand the science or actually the mechanism that how you explain the reason for certain constitutive outcome in, at least for the solid mechanics, like why do we have an earthquake? Why is the sleep suddenly? Why is the fault suddenly reactivate? We need a reasoning, and that reasoning can be established in a graph, but not so much when we only have a focusing machine without any intermediate entity for us to create the human understandable logic. So I think this is two reasons, but not to take away the fact that a lot of time a black box model that are very accurate has its own values and can be very efficient in some other situations.
Yeah, so I think the second reason that you mentioned is about interpretability, which I think is very important for mechanics. Yeah. The first one, actually, in my group, we have something we call DeepONet, which is we approximate functions and operators, not just functions. So that's very different. So that actually facilitates this. But I was wondering if Enrui, do you have a question for Steve?
Yes. I'm.
Go ahead, Enrui.
Yeah, I still have some question over the graph, and yeah, I'm wondering. So, in case you keep training this structure, will you finally get a complete graph? Because I think that doesn't hurt the score in any way. So
yeah, okay. So this is also a very interesting thing. So I don't know whether I have that figure. So this is actually training. So one thing that are interesting is that adding more nodes doesn't necessarily improve the score. And the reason, and also there is another interesting thing that we discovered recently with our collaborator is that also from Johns Hopkins, actually, is that the direct graph actually, the determined direct graph would optimize the prediction values, but adding all of the connectivity don't necessarily make the predictions better. The reason is the following. And one of the possible explanations is the following. Suppose that the fabric tensor, there's a fabric tensor here that are somehow related, or but then predicting the fabric tensor could be the cause of the changing of the tractions. But if predicting the fabric tensor is much harder than actually predicting the tractions, then even though this is the right causal mechanism, you linking it, it will make the prediction. It may not actually give much improve on the predictions. So our goal is to generate a predictive graph that actually improves the prediction. So so the game, we don't actually make any requirement. We let the game explore, and oftentimes we don't actually necessarily find that we would actually connect all the graph in every possible way. For that simple reason, some of the edge will not increase the performance, and that would another thing that if you another interesting thing is that can we actually, if we don't want to create a very complex graph, is there a way to actually simplify the model? And the answer is yes, because you can actually set the revolve involving the execution time, or actually simply penalize again a very complex network, and you can actually create a simpler network that make the prediction as well.
Mm-hmm. Okay, I see. And also, so for the nodes, the intermediate nodes, so we don't have any label for any of these, right? Or for part of this?
Oh yeah, here, this is actually the interesting part. I call it label, but the label is actually the strategy. So why is it a label graph? Because without we actually have multiple label, and we pick the label, and the label is actually the specific model that we actually put into generating the mapping from the upstream to downstream. Okay, if you don't put the label, you will get the direct graph that gives you the relationship to make the prediction, but you don't know exactly what model, what strategy you want to move. So we put the strategy to calibrate to actually create a mapping from the input to the output as a label. So the game actually do two things. We actually try to find out the connectivity, and then we put the right label there. So there are two options that are simultaneously in place. And then we connect it in the right way, put the right label, which is the strategy to mapping it. And then that would be the right combination of the action we want to make the predictions. So it's also completely possible that eventually the computer will find out that the black box is the best options. We haven't seen it yet, but that is highly possible. We don't discriminate against whether we need to put more mechanism or make it simpler. We just let the game find out which way is the best way to optimize the score.
Okay. Yeah. Thank you. Thank you very much.
So Andrew, who just asked you, is working on tissue biomechanics problems. So he's trying to develop this type of constitutive equations from data using different methods. So I was going to ask you if your codes are open source. Are they available, or because it's very difficult if we want to compare? It's very difficult to write all this stuff.
Yeah. So the reinforcement learning. Yeah, we are planning to doing it. In fact, we are planning to initially we're planning to have a short course for the WCCM at Paris, but that was delayed due to the coronavirus. But we do have plan to actually have a plan to make it open source and also provide some initial training. Maybe we'll create a video or so, because I think this reinforcement learning are actually quite hard to implement and quite hard to use. Like George, what you correctly point out. Yeah, but we do have a plan to do that. Hopefully, maybe in the spring semester, so we can do that.
All right. Thank you very much, Steve. Kelly, do you want to wrap this up?
Yes, I think it's time to move to the second talk. And again, thank you very much, Dr. Sun.
Thank you.
For presenting this very interesting research work.
Yeah, thank you for the invitation. I appreciate it.
So now we can move to the next talk. So first, you can stop sharing. So, okay, great. So the next speaker is Dr. Lee. Daniel Lee is the Vice President of Convergence Science. Convergence Science is a fast-growing